Let's imagine a completely insulated empty room. Now let's place a refrigerator in the room and connect it to a power supply. The refrigerator is operating normally, but here's the twist. We'll keep the refrigerator door open so that it is extracting heat from the entire room. What do you think would happen to the temperature of the room after a certain time? Do you think the temperature would increase, decrease, or stay the same? Go ahead, pause the video and see if you can get to the solution. The problem itself is quite interesting. At first glance, it may seem like the room's temperature will go down as the refrigerator extracts heat from its surrounding. But for those of you who think that the temperature of the room would actually go up, well done. With the given assumptions, the temperature of the room will indeed go up. Before understanding why this happens, I want you to take a step back and think about the first law of thermodynamics. Most of us have learned this in our school as the law of conservation of energy. In other words, energy can neither be created nor destroyed, it can only be transferred from one form to another. Even after knowing this definition so well, we often find ourselves struggling to apply this to real-world examples. And I think there is a really good reason for it. When talking about the first law of thermodynamics, I think there are two important things to know: energy, and how energy interactions take place from a system to its surroundings. Many of us lack the clarity of what energy exactly is and how it is exchanged between a system and its surroundings. Before I start explaining energy and energy interactions, I want to quickly point out that we'll be using the terms system, surrounding, and boundary throughout the video. A system could be thought of as a part of space that is of our interest. In our problem described earlier, it is the temperature of the room that we're interested in predicting. So room is our system, and the rest will be the surroundings. A boundary could be physical or imaginary that separates the system from its surroundings. In our case, it's the walls that are separating the room from the rest. So the walls are our boundary. Also, for the sake of simplicity, we'll restrict the examples to closed systems, meaning we'll not consider any mass flow across the boundary of our system. Let's now try to understand how energy can be categorized. In broad terms, energy can always be categorized as kinetic energy and potential energy. The energy associated with the motion is called kinetic energy, whereas the energy associated with position is called potential energy. Potential energy can also be thought of as stored energy. That is something that has a stored potential to be converted into kinetic energy or some other kind of potential energy. When we talk about system, we can talk about energy associated to it in two forms: macroscopic and microscopic. A system's total energy is the sum of these two forms of energy. And what is macroscopic and microscopic energy? Let's consider an example of a helium balloon floating in air at a certain height and traveling upwards with some velocity. If you observe the balloon from an external fixed reference frame, the balloon has two types of energy: kinetic energy due to its velocity and gravitational potential energy due to its height. A system could possess several different types of potential energy like electric, magnetic, and elastic potential energy. Although these types of energy just arise in special cases, so we'll not consider these energies in our discussion. Don't worry if you're not familiar with all the forms of potential energy. At this point, I simply want you to know that potential energy can exist in several different forms and not just as gravitational potential energy. The second classification is the microscopic energy. Microscopic energy can be viewed as the sum of kinetic and potential energies of the molecules. The sum of all microscopic forms of energy of a system is called the internal energy of a system. This is one of the most important terms that you will often come across in thermodynamics. Internal energy can be classified into four different components, and these are sensible, latent, chemical, and nuclear energy. The part of the internal energy of a system associated with the kinetic energy is called the sensible energy. Temperature is the measure of average kinetic energy of the molecules. Therefore, in a way, we can say that the temperature can be sensed by a thermometer, hence the name sensible energy. Latent energy, on the other hand, arises during the phase change processes. For example, consider boiling of water. At 100 degrees Celsius at sea level, the water temperature stays constant during the boiling process. However, we're still adding heat to the water to convert it to steam. This energy that arises during the phase change process cannot be sensed using a thermometer. Hence, it's called hidden or latent heat. The chemical energy of a system is due to its atomic bonds in the molecules, and it only comes in picture during a chemical reaction, for example, during the burning of fuel. Nuclear energy exists due to the strong nuclear forces within the nucleus of an atom. This energy comes into picture only during nuclear reactions. So now that we know all the components of energy, we can say that the total energy of a system is equal to the sum of kinetic and potential energies at the macroscopic level and the sum of kinetic and potential energies at the microscopic level. As we just saw, the sum of kinetic and potential energies at the microscopic level is nothing but the internal energy of the system. Now let's assume we want to change the total energy of the system. In case of our balloon, if you want to increase its total energy, according to this equation, we can do it in three possible ways. Either increase its velocity to increase its kinetic energy, or increase its height to increase its potential energy, or to increase its internal energy. The change of the total energy of a system can be written as final energy of the system minus its initial energy. If we assume that the balloon is flying at a stationary height, the only way its energy can be increased is by increasing its internal energy. As we saw, internal energy has 4 different components. Let's say at the given temperature and pressure, the helium balloon cannot undergo a phase change process. Its chemical and nuclear energy also stay the same. So the only way to increase its energy now is by increasing its temperature. Let's take another example of some water in a pot. If we consider the water to be our system, and if we want to increase its energy, given that the water pot does not change its position, the only way to do this is by increasing its temperature. So now the question remains, how can we increase the temperature of the water? Well, one simple way is to just use a gas or electric stove so that we create some temperature difference between the boundary and the system. This temperature difference results in the heat flowing into our system. Now I want to draw your attention towards the fact that the boundary of our system is at a different temperature due to external heating. If there were no temperature difference in the boundary and the system, there would be no heat transfer. The heat transfer can also be prevented by having a perfect insulator around our system. A perfect insulator prevents the heat flow through it even when there is a temperature difference between the system and the surrounding. The key learning I want you to take from here is that for a heat transfer to take place at the boundary of the system, a temperature difference is always needed between a system and its surrounding, and the boundary should not act as a perfect insulator. So now we have seen how we can add energy to the system by heating the surrounding of the system. But there is another way in which we can add energy to the system when there is no temperature difference between the system and the boundary. This way is called work transfer. Let's imagine that the pot of water is perfectly insulated. Now we take an electrical heater and place it in the system. If we switch on the heater, the temperature of the water rises, leading to an increase in the energy of the system. Now this may seem like we're cheating by just producing thermal energy inside the system instead of the surrounding to heat the water, but that is how work is defined in thermodynamics. If there is no heat transfer across the boundary of the system and the energy of the system is still changing, this kind of energy transfer is called work. And there are only 2 ways in which energy can be added to the system, in the form of heat and work. Just a side note here that work does not always have to be electrical. In the above example, if we put a paddle in the system such that it is submerged in the water, and if we rotate it externally, we can still see temperature increase in our system. So work can exist in several different forms, and mechanical and electrical work are only 2 kinds of work. Now let's say we add 200 kJ of heat to our system. We can say that the increase in the total energy of our system is equal to the amount of heat added to our system. Similarly, if we say that we add 200 kJ of work to our system, we increase the total energy of our system by 200 kJ. We can also increase the energy of our system by partial addition of heat of 100 kJ and work of 100 kJ. The energy balance of our system now looks like this. And if you have noticed, we treat 200 kJ of heat and 200 kJ of work equal when we add it to the system. This was first observed by Joule in his famous paddle wheel experiment during the 1840s. Adding 200 kJ of heat would yield the same temperature increase in our system as adding 200 kJ of work, and this is the first law of thermodynamics applied to a closed system. All it says is how energy of a system can be changed and how we can mathematically describe this energy exchange. Now going back to our problem, we can identify that the room is perfectly insulated. So the type of energy exchange between the system and the surrounding is work exchanged due to the electrical work crossing the boundary of the system. If we know that the work is crossing the boundary, we're adding energy to the system. And if we're adding energy to the system that is stationary, we're increasing its internal energy. As we see, the air in the room is not changing its phase, neither is it undergoing any chemical or nuclear reaction. The refrigerator is a device that does not in any way store this energy once it reaches a steady state. So the only way we can add energy to the room is by increasing its temperature. Having said that, can you think of any other way that you can add energy to the system? Given that you can replace the fridge with some other device, but under the condition that the temperature of the room should stay constant. Comment your answer down in the comment section.